Okay. Thank you very much. I'd like to thank the organizers for putting together this wonderful meeting. I realize that I'm the last speaker of this session. So I'm the person who's standing between you and a relaxing Saturday evening. So I'll try to make this as painless as possible. I should mention that maybe this title is a bit of a misnomer. What I should have really said is boosted one-dimensional superconductors, because I'll be talking about a system of paired fermions. But hopefully, that's not such a big problem. This is work that's been done with Shani Rai, who is a PhD student, and Vijay Shenoy, who's not. The work is still, it's being written up and it should be up on the archive soon. So what is it that we are looking at? So what I'll be talking to you about is a boosted one-dimensional superconductor. I'll explain what I mean by a boost in a second. But before I talk about one-dimensional superconductors, let's see what we know about boosted conventional superconductors. So what is a boost? So by a boost, I mean that you take a superconductor or even a superfluid and you give it a certain flow velocity when it happens to be in a pipe or something like that, and then ask what happens to the superfluidity or the superconductivity as a function of that flow velocity. Alternatively, you could think of something which is moving inside the superconductor or the superfluid and ask what happens again to the excitations which are created inside the system when there's something moving with a certain velocity. What happens as a function of that velocity? So that's what I mean by a boost. And so what we know is that beyond a certain critical velocity, superconductivity is destroyed. And you can ask what happens, how this thing is destroyed in conventional superconductors, by which I mean those which are not in one dimension, which are described by something like a mean field theory. And there we know that there's this concept of a Landau critical velocity, which happens to be really either the minimum of one of these two quantities. Vs here is the sound velocity of bosonic collective modes inside the superconductor, modes that have to do with the superconducting order parameter. And this is a velocity that you can extract from the single particle fermionic excitations. And then whichever one of these is smaller, and it's almost always typically this one, that ends up being the critical velocity at which superconductivity is destroyed, in the sense that the superconducting gap goes to zero. So it decreases with the size of the boost, and it goes to zero at Vc. So this is sort of the traditional way of looking at the critical velocity of a conventional superconductor. But now we ask the question, what happens if the gap in the superconductor is zero to begin with? Okay, if there is no notion of a gap inside the superconductor. And that's what happens in 1D superconductors. And I'm talking about one-dimensional superconductors at t equal to zero, and I'll tell you why that's important in a second. So the Merman-Wagner-Coleman theorem, which you're familiar with, presumably tells you that there's no long-range order at t equal to zero, so that tells you there's no superconducting order parameter. But what happens is that you can have algebraic long-range order in the system, which means that the correlation function of the superconducting order parameter decays as a power law with distance. And as a result of this, even though there is no superconducting order in the sense of a non-zero order parameter, there is still a finite superfluid stiffness, and the system can support dissipation-less currents. Okay? So the question that we're asking is, what does a boost do to this kind of superconductor? So that's really the main question asked in this talk. So before we look at what a boost does to this kind of superconductor, let's try to understand how we even look at a one-dimensional superconductor in which there is no true long-range order. And so it turns out that that is most efficiently done in the language of Bosonization. So when you take a one-dimensional interacting fermionic system, it turns out that the right way to look at excitations about the ground state is not in terms of single particle fermionic excitations, but actually collective particle hole excitations which look like bosons. And then one can write down a Hamiltonian in terms of these bosonic excitations, where pi and phi are two fields which correspond to these bosonic excitations. And corresponding to this Hamiltonian, one can also write down a Lagrangian in terms of just the phi field alone. So what is important here is that all the physics of this fermionic system is sort of now contained in these two parameters, K and V. V is not so important. It's sort of related to the Fermi velocity with some contribution from the interactions. But K really is the important parameter here, and K is what's called the Luttinger parameter. So this is also called Tomonaga-Luttinger liquid. And it turns out that these two fields, pi and phi, correspond to two different things associated with the bosonic field. This one corresponds to the density of the bosons, which also is related to the density of the fermions. And this one corresponds to the phase of the bosonic field, which is related to currents that can be carried by the fermions, ultimately related to supercurrents. So now you can see that you can either twist the density or this particular object, which contains in it the phase. So you can either twist the phase or the density. And the stiffness for each of these is k or 1 over k. So the dominant order in the system will correspond to whichever of these two stiffnesses is higher, meaning whichever you need to you need to put in more energy to twist, that is the dominant order, which is also reflected in the way that the correlation functions for these two kinds of orders decay with space. So when you put a twist here, it is like looking at superconducting order, and when you put a twist here, that's like changing the density, and that's like looking at charge density wave order. And so you don't have either long range superconducting or charge density wave order, but you do have this kind of algebraic order with a twist, with a stiffness associated with both kinds of orders, and correspondingly the correlation functions decay like this. So if k is greater than 1, which incidentally corresponds to the case of attractive interactions, you have dominant superconducting order. This correlation function decays slower. And if k is less than 1, then you have repulsive interactions and you have dominant CDW order. Okay? So now let me define what I mean by a boost and how you can apply a boost to a system like this. So my definition of a boost is that I take the momenta of the fermions and I just change the momentum from k to k plus u. Okay? So what does this do? So what this does is, in general, it can give you different speeds, Fermi speeds, for the left and the right movers in the system. So remember, it's a one-dimensional system. The fermions at the Fermi energy can either move left or right. And when you boost like this, you can in principle have different speeds for the left and right movers. How different the speeds are will depend on the exact dispersion, how the energy is a function of momentum. What will happen in general is that the left and the right movers will have different speeds, and so there's an average speed, which is this VFU, and then one of them is lowered compared to the average speed, and the other is raised compared to the average speed, and that's given by W of U. Okay? So to look at this more schematically, in the absence of a boost, left movers and right movers have the same Fermi velocity, minus kf and plus kf. So the Fermi surface is basically something which extends from this point to that point. Now, when I introduce a boost to the system, which you can also think of as having different chemical potentials for left and right movers, what I'm doing is I'm actually moving the Fermi C from lying between these points, minus kf and plus kf, to something which looks like this. So this now lies between some point here and some point there. So the momenta of the Fermi momentum of the left mover is not the same as the Fermi momentum of the right mover, and correspondingly the Fermi speeds are also different. Okay, so one can then do the bosonized theory for this kind of boosted system, linearize about the Fermi points, write down an effective bosonic theory, and it turns out that it looks like, the Hamiltonian looks like what we had earlier, but with the fact that the Luttinger parameter now develops a dependence on the boost u, as does this velocity which is sitting in front, but also what happens is that there's a term which couples the pi field and the phi field, which was absent earlier. Now it turns out that the second term is not so much of a bother, because you can actually, when you derive a Lagrangian from the Hamiltonian, which you'll be using to calculate the correlation functions, you can actually write down a Lagrangian which looks pretty much like the Lagrangian of the unboosted system, but in terms of new fields phi tilde, which can be written in terms of the old fields, but with the space and time coordinates space and time coordinates transformed according to a Galilean transformation with speed W of U. So basically, you boosted the system that corresponds to a Galilean transformation, and the Galilean transformation is basically something on the fields. So this still gives you a Lagrangian which looks the same. So the important physics is in this Luttinger parameter k of u, which now tells you, so because the Lagrangian still has the same form, the correlation functions will still decay in the same way, but with a Luttinger parameter which depends on the boost u, okay? So here is now the important thing, perhaps the most important slide here. So it turns out that the Luttinger parameter is just a function of the average Fermi speed, the average of the speed of the left and the right movers. And so this average speed is an even function of the boost. It doesn't matter whether I'm boosting to make the left movers move faster or the right movers move faster. The average speed shouldn't depend on that, okay? So then I can make a Taylor expansion of k of u in terms of u. And so the lowest order term is going to be u squared because it can't depend on u, and it's going to look like this, okay? So here's the important thing, that when you look at this derivative, how the Luttinger parameter depends on the average Fermi velocity, it is less than 0 when k is greater than 1, and greater than 0 when k is less than 1, okay? And when this is when the second derivative is equal to 0, then k of u is equal to k of 0, okay? So what is all of this telling us? So the second statement tells us that the boost has no effect when the dispersion is just parabolic, okay? Because you're not really breaking Galilean invariance, it has no effect, okay? So you need to break Galilean invariance, so the simplest thing that you can do is put the system on a lattice, and that gives you a dispersion like this, which tells you that d2f du squared is less than 0. Now why is this important? So this is important because it tells you that k of u is greater than 0 when k was greater than 1, k of u after the boost is greater than k when k was greater than 1 to begin with, and k of u was less than k when k was less than 1 to begin with. So what does this tell you physically? It tells you that if superconductivity was dominant to begin with, then the boost is actually strengthening the superconductivity. It's making the correlation functions decay slower, which is completely the opposite of what you would normally expect when you boost, which is that it weakens superconductivity. But here it's actually strengthening superconductivity, which is really sort of the main result of this analysis. And similarly, if the dominant order was charge density wave order, then that is strengthened upon boosting, okay? And the same also happens with spin half fermions. We're looking at a system of spinless fermions. So, you know, even though the analysis that was presented was for small u, we can do it analytically for all values of u, and this fact remains the same, that superconductivity is strengthened upon the application of a boost. So since I'm running out of time, let me just very quickly tell you just one other thing, which is that since we're introducing a lattice, one of the things which happens when you introduce a lattice is you can actually destroy this Luttinger liquid by opening up a gap due to Umklapp. And so we've also looked at that situation, you know, what happens when you apply a boost, when you have Umklapp and when there's a gap. And it turns out that, okay, let me just quickly go to my conclusion slide then. Sorry, okay, anyway, so if we just skipping over all of that. So it turns out that what happens is that when the system can have a gap without a boost, the boost can help to either make the gap larger or actually close the gap, which can give you interesting, you can go from gap to gapless phases just by applying a boost. So these are my conclusions. That, you know, so the main conclusion in some sense is really the second one, that for a simple lattice dispersion, a boost can really have the counterintuitive effect of strengthening superconductivity, making the superconducting correlations decay slower than in the absence of a boost, which is quite the opposite to what happens in higher dimension. Thanks.
Yes, thank speaker. Time for questions.
Yeah. Here, if I understand, you know, you put the boost by hand in your Hamiltonian, right?
Sorry, putting what?
I mean, in this here, I mean, you are putting the boost by adding this extra term in the Hamiltonian, right? But how do you actually, in physical system, how do you?
Okay, so that's a good question. So in the physical system that we have in mind, it's really a system of cold atoms, where it is possible by introducing artificial gauge fields to actually have a different chemical potential for right movers and left movers.
So I had a similar, and it's a related question. So can we think of, for example, you prepare the system, let's say in, you know, 1/2 of the semi-infinite line, and then you just release it so that the front actually moves forward with the velocity or something.
Right. Well, I think so are you saying that you have movers of just one kind and not both kinds? Well, I think for this you would need left movers and right.
It's a special kind of thing when mu L is 0 and mu R is some constant.
Right.
You know.
So, okay, so the reason that I'm a little, you know, I don't understand that very well is that, you know, so this is something where you need both left movers and right movers. Now, if let's say you boost such that you lose one family of movers completely, then you're going to a point where one of them has sort of, zero velocity, and then I can't really bosonize about that anymore. So I don't know if there's any problem with that. Kedar, you had a question?
The lattice played a role so that the system knew it was on the lattice.
All right. Okay, just let me answer your question.
Is it the cosine or?
Right. Okay. So up to this point, there was no lattice.
Yes.
And the point is that, so if I want the boost to have a non-trivial effect on k, meaning k of u to be different from k of 0, then I want this term or higher order derivatives to be 0. Okay? So if I had a dispersion which was just p squared by 2f, then that wouldn't happen because this second derivative would be 0 and all higher derivatives would be 0. So I need a dispersion which is different from p squared by 2m. And the simplest way in which I can do this is by putting it on a lattice so that E...
And is that simply the statement that the boosted system has no idea that it's boosted unless there's a lattice?
Exactly. Although one has to be a little careful because I don't even need a cosine dispersion. I can have a relativistic p to the 4th dispersion which will also do this, and there you probably can't think of it.
Okay, last question.
So bosonization generally it relies on linearization of the spectrum, right? So that doesn't get affected with this, is it?
No. Because of the fact that, what's happening here is that you're just moving your Fermi points from earlier being minus kf and kf to now being minus kf plus q and kf plus q. But you can still linearize about those points. The place where you can't linearize is down here, which is related to Satya's question, because if you boost it so much that the left movers move all the way down there, then there's a problem.